Hello, this is Scott Dahman of PowerWorld Corporation. In this section, we'll take a look at some principles of linear programming optimization and how they are used in PowerWorld Simulator's OPF tool. Okay, so as we mentioned in the last section, the software uses linear programming methods in order to do the optimization because it's well suited for determining binding constraints, and it just works well for electricity markets. So we'll review the concepts so that we understand how it works, and then also how some of the displays can be used inside the OPF results. This equation right here, this is a scalar value for z is like what we're trying to minimize. And you can think of, in the case of the optimal power flow where we just have generator controls, the total cost is simply a sum of all the costs associated with each unit times the output of the unit. So the x are the control variables. You can think of that in the simple case where only generators are controls. It's the megawatt output of each generator. And then there's a cost associated with that megawatt. So the total cost of operating the system is just the sum of all those products together. So this is a vector, a vertical vector, and this is a horizontal one, and then the result is just a scalar. And then the constraints are shown as also as a function of the controls, and they can be equality or inequality constraints. So for example, in the case of an area power balance constraint, it can just be the sum of all the generation in the area has to equal some constant, the load plus the losses if there are losses. If you have a transmission line constraint, it would be an inequality constraint, and you can have a sum of the A's would be sensitivities times the output of the generators, so shift factors times the generator output, and then all of that would have to be less than or equal to a limit. So, and then you can show this in matrix form as the A matrix times the X vector of controls, the same X that you see up here, equals B, which is the right-hand side. So all the area power balance constraints and limits and things like that. And as we'll see, this gets formulated so that all of the inequality constraints become equality constraints, and it gets formulated with slack variables. So you end up really with this in the form of AX equals B. So just looking at the 3-bus example that we looked at earlier, where we have 3 generators, but at the generator bus 1, 2, and 3 with costs of 10, 12, and 20 respectively. What we're trying to minimize is 10 times the output of generator 1 plus 12 times output of generator 2 plus 20 times the output of generator 3. That's the total cost. And then the constraints, the total generation equals the total load for the area. And initially we looked at it and it was 180. And then the 0.66 and the 0.33 are sensitivities that are associated with binding constraints. And it's 0 so if a constraint is binding, then it becomes part of the formulation. For the other constraints that are not binding, for lines that aren't at their limit, there's no consideration of the sensitivities. We only look at the ones that are binding. And of course, as we mentioned earlier, as it goes through the process of solving, there can be new constraints that get added or removed from the problem. So that can change. But really, we only care about the sensitivities with respect to lines that are binding. And then there's also an inequality constraint for the minimum and maximum output of the units. If we assume that each unit has a minimum of 0, then it's got to be greater than or equal to 0, and also less than or equal to the max, but that's not shown here, just for simplicity. So we can look at this problem graphically too. And it's easy graphically, we can really only look at things at 2 dimensions at a time easily. So the 2 dimensions that we're considering are just the output of generator 1 and the output of generator 2. For the moment, we're ignoring generator 3 as a control. And really, if a control is not a marginal control, you can't ignore it. So controls in the actual system, any control that's at a limit is not a marginal control because it cannot provide a marginal megawatt. So if a unit is at 0 or it's at its max, then it's really not part of this formulation. So the generator bus 3 is not part of the formulation at the current operating point, but it could become part of the formulation if we have unenforceable constraints. But again, just to simplify things, we can represent the power balance constraint by this line right here, which is P1 plus P2 equals 180. That's the load. So that constraint can be satisfied by an operating point that's anywhere on this line. So at one extreme, we could get 180 megawatts from generator 2 and 0 megawatts from generator 1. Or at the other extreme, we could get all of the power from the other generator at 1 and none at 2, or anywhere in between. So anywhere on this continuum would satisfy that constraint. The other constraint is for the transmission line, and that's an inequality constraint. And then these are the sensitivities associated with the binding line. So 0.66 times output of 1 plus 0.33 times the output of 2 has to be less than or equal to the limit at that line. So that's represented, this line is the boundary, and then really the whole region underneath here is also satisfies that constraint. So the other thing is that the objective function for each operating point along here is shown by the orange number here. So again, if we're ignoring for the moment, because we're looking at this in 2 dimensions with 2 marginal controls, 10 times the output of generator 1 plus 12 times the output of generator 2 is the total cost. So if we get all of our power from the expensive generator, it has a cost of $21.60. Oh, the other thing too is really the intersection of the 2 constraints is what's called the feasible space. So really we want to operate somewhere on this line because that's the intersection of the 2 constraints. This one is everything underneath here, and this one is everything on the line. So our solution is going to lie somewhere on here. The trick is then just to pick the lowest cost. And as we'll see, one of the theorems of linear programming basically states that if you have a binding constraint, then you're going to want to be on the vertex of that. So where we end up, the solution point is actually right here, because that's the lowest cost, 1920 versus 2160 for being over here. That's the lowest cost along that line. We want to get as much power as possible from the cheaper generator, generator 1, but we can't go beyond the purple line because that violates the constraint. So we end up here for the solution. So the linear program just mathematically tries to find the vertex in that solution space that has the least cost. And of course, in a larger system with more marginal controls and more binding constraints, this becomes like some multi-dimensional polygon that you can't really plot on paper, but it's basically doing this in many more dimensions. Again, looking at the linear program, it's trying to minimize a cost function where you have n is the number of controls and m is the number of constraints. So you have a different row in this equation for every constraint, and you have a different n is how many controls you have, typically generator controls. And typically in a power flow solution, you have a lot more controls than you do binding constraints, which is good. That means we can move, we have a lot of options for moving generation around to relieve our binding constraints. So that's why it means that this matrix right here has lots of columns and just a few rows by comparison. The next few slides, again, just kind of talk about formulating the problem. I won't go into great detail on this. It's saying that a vector is basic if at most m components are non-zero. So m, again, is the number of constraints. If we have the number of constraints that are equal to the number of controls, then this becomes like a square matrix up here of basic variables, and the non-basic variables don't matter. They're non-binding, and they have the components are all zero. So what the algorithm does is it arranges the variables in the matrix so that you've got basic components in one partition of the matrix and non-basic components in the other. And it's saying that the basic component of the A matrix must be non-singular, which means that you can invert it. In the scalar sense, it means it's not equal to zero. So in the matrix sense, it means you can invert the matrix and then solve for the control variables equal to the inverse of that matrix times B, so that you can get a solution for what, for example, all your generator outputs should be. Okay, here's just a mathematical example that it's not related to any power system that we looked at, but there's an infinite number of solutions to this set of equations, but there's only one solution if we assume that one of these control variables is zero. So, here we have two equations and three unknowns, x1, x2, and x3. And if we assume one of these is zero, then we can solve deterministically for the other two. So as long as the matrix is non-singular, in other words, the equations are independent, we can invert the matrix, then we can solve for the other variables. So if we assume x3 is zero, we can solve for x1 or x2, and then kind of the same thing if we assume the other twos are zero. We can get to a solution if we can satisfy these constraints down here. Okay, another feature is if we transform the variables into this what's called a canonical form, then we can just read the solution. In this case, anything that's not shown as 1 right here is actually equal to 0, and then these are non-basic variables that don't matter because these controls are associated with 0. So if we read the set of matrix equations, this just says that x2 equals b1, x1 equals b2, and x3 equals b3. That's what we get out of there. So we convert everything to, if we have an inequality constraint, we convert it to an equality constraint by using a slack variable. So for example, if we have a generator limit that has to be between 50 and 100 megawatts, then we can write two equations, two equality equations instead of this inequality. Right here we can have a slack variable that we add to the output that gets us to 100, and then one that we subtract that gets us to 50, where all of these variables are greater than or equal to 0. So then that enforces the limit. Okay, so getting back to our power system example, the objective function is minimizing, again, 10 times P1 plus 12 P2 times plus 20 P3, where the power balance is met and the transmission constraint is met, and that's changed into an equality constraint by adding this dummy variable here, and then all of the variables are greater than or equal to 0. So the x is the P1, P2, and P3, and the s is that slack variable. So, and then it looks like this. So the 100 is the limit, the 180 is the power balance, and then these are the coefficients associated with P1, P2, and P3. So, and then this is the cost vector right here. Okay, so this is the theorem that it uses. So the A matrix has these dimensions. The rank M means it has M independent equations. So it's basically an M by M that gets inverted. And if we have a feasible solution, we have a basic feasible solution. So that's the one that we want to look for. And then we want to optimize it such that we get the lowest cost. In other words, to find the optimal solution, we just need to look at the set of basic feasible solutions. So what that means, like graphically, is this is a basic solution, and this is a basic feasible solution here at these vertices. So what it means is algorithmically, we just need to look at these vertices and find the one that has the least cost. And if we're starting at this vertex right here and we see that we can reduce cost by moving to an adjacent vertex, then we'll do what's called a pivot and move from one point to another until we get to a point where we can't move to another feasible vertex without reducing the cost. So that's what it does. Okay. So it's used what's called the Simplex method, and I'm not going to spend too much time on the math in here, but the slides are in here. So yeah, just like I said, we've got the feasible space, and what we want to do is we want to find the vertex that has the least cost. So, and to do that, you start at one vertex basically by, you put the slack variables in so that we're feasible. If there's a transmission line that's overloaded, it's going to have a very high cost associated with it, so we're going to want to move away from that vertex to another vertex. So this shows, it formulates it by just mashing all these numbers into a single matrix. And then what we can do to pivot from one solution to another, we just normalize these variables, and then we can switch variables from the basic to the non-basic side and vice versa until we find the least cost. So that's called pivoting. What it's going to do is it's going to look to see if making a change in what's in the basis will get us to a vertex with a lower cost. And if so, it'll make that change. If not, then it knows that it's done. Like I said, if you know, to do the pivot, it's basically going to first identify an element to pivot around, and it does that by looking at costs. And that's kind of shown in the subsequent slide. But if we assume that we're going to pivot around this point right here, then what it'll do is normalize that variable so that it's equal to 1 by either multiplying or dividing the entire row by a constant. In this case, it's already 1, so it doesn't need to do anything. And then zero out all the other columns by taking linear combinations of those equations. So you can zero this one out by taking negative 1/3 times this row and adding it to this row. Then we've come up with different equations, but we haven't changed. We've come up with different numbers, but we haven't changed the set of equations. So taking negative 1/3 of this and adding it to this gets you a 0 right here, and these numbers change accordingly. So then it's pivoted. So the method basically uses a technique described here, which I won't go into in great detail, but it's seeing you know, how we can move from one vertex to another in order to reduce costs. So, and then there's a reduced cost vector right here that's included in this minimization function. And by computing those, then it knows if it needs to pivot or needs to move different variables into the basis. So again, here's an example with a reduced costs appended down here at the bottom, and then set of basic variables and set of non-basic variables. If any of the non-basic variables have reduced costs that are positive, what it'll do is it'll pivot on the most positive one. So it's basically, again, looking for a neighboring vertex that reduces the objective function cost the most. And if any of these are non-zero, then it's going to pivot to that vertex. If not, then it knows that it's done. So again, there's more. It sets up the numbers, and then if there is a reduced cost that improves the objective function, then it'll pivot there. In the initial formulation of the unconstrained problem, so where all we have is the power balance constraints, P1 plus P2 plus P3 equals 180. If we're starting out with 180 coming out of generator 1, that's the cheap one, then there's really nothing to do. The reduced cost vector, all the costs are bigger than zero, so we can't reduce them by moving to a different vertex, so it quits right there. If we add the transmission constraint to the problem right here, and again we make it an equality constraint by adding a slack variable, then what it does is it computes the reduced cost vector down here at the bottom, and the one associated with this row right here has the most reduced cost, so it's going to pivot on there and move those variables into the basis. And then so what it does, it does a normalization and then zeroing out of all the other columns, and then computes the new values. And we have P1 and P3 in the basis here, but that's not optimal. We still have a negative reduced cost at that point down here, so it pivots again. And then the next iteration gets it to the vertex where P1 equals 120 and P2 equals 60. And then that's the solution point that it settles on. So again, that's the graphic from that. And if we want to see some of these quantities in there, so let's go back to that case. Go to File. Just for my recent file list, I'll pick the B3 LP. And if I go to Add-ons ribbon and then go to the OPF options and results, and then I choose on the constraint options, I clear the checkbox for disabling line and transformer MVA enforcement, and then solve the LP. So I get to that solution point. If I look at under LP solution details, the LP basis matrix, then it has one row for each of the constraints. So the first constraint is the power balance constraint for the area, and it has the lambda associated with it. That's basically the cost of that's the least cost unit in the area, is the $10 per hour one. That's the cost of enforcing that constraint. And then there's also the shadow price for enforcing the line limit constraint, which is equal to about 6. And then it also shows the sensitivities of the marginal controls with respect to that. And these are all, the sensitivities are all assuming that power is withdrawn from the slack bus, so there's no sensitivity shown here for generator 1 because it is the slack bus. But generator 2 is negative 1/3. And that's just the shift factor that's saying if I increase power here and withdraw it at the slack bus, 1/3 of it will go from bus 3 to bus 1. And so it's negative because the line's actually referenced from 1 to 3. So the incremental power goes in this direction, but the line's referenced in this direction. So that's the sensitivity associated with that constraint. Yeah, and you can also right-click in here and choose the option to show the full tableau, right here. And then that shows the sensitivities for the other controls as well, even though they're non-basic controls. But you see those. So that's just the basis matrix. So the marginal controls are just generator 1 and 2, not generator 3. That's not in the basis. It's not a marginal control. And then any binding constraints are going to show up in the basis. If there's a constraint that's non-binding, then it doesn't matter. It's ignored. Okay, yeah, so those are the basic variables. And then you can see the sensitivities there with respect to withdrawing power at the slack. Okay, so we can also use these equations, and again, it does this internally. You don't really need to know this other than if you're interested in how it calculates it, but it can use the solution point to calculate then the marginal cost, or the lambdas. So again, the $10 per megawatt hour is just the least cost way to export power from area 1, and that ends up being one megawatt from generator 1 times the cost of incremental cost at that generator, which is $10 per megawatt hour. That's for the area constraint. For the transmission line constraint, it uses the sensitivities, and it solves for the delta P1, delta P2. And as we saw earlier, if we increase the flow on the line by 1 megawatt, but hold the power balance constant, so this is the power balance up here of 0, and we increase the line flow by 1, and then we solve for the delta P1 and delta P2, we get generator at P1 goes up by 3 and one at 2 goes down, so it saves $6. So you get the -6 right there. Okay, and you can see those quantities on the inverse of the LP basis tab right here. Okay, and then once it has the marginal cost of the constraints, then it can calculate the LMPs. So the LMPs is just the sensitivity times the marginal cost of the binding constraints. So for each of the 3 buses, we have these are the power balance sensitivities. They're just all 1 for each of the generators. These are the line sensitivity constraints, and then the marginal cost of enforcing power balance and the binding constraint. And so we just multiply those matrices together and get the 10, 12, and 14. And you can see those if you go to the under results, bus megawatt marginal price details. That shows you, make this a little bit bigger. Yeah, we looked at that earlier, the cost of congestion, energy, and losses, and then the impact from enforcing the area constraint and then the line constraint. So you can kind of think of that as, $10 comes from the area constraint, and depending on what bus you're at, there's an impact of either 0, 2, or $4 from enforcing the line constraint. And then you can also, another display in here is the bus marginal controls. And that just explains like where, we looked at this earlier kind of intuitively. If we want to get a marginal unit of power delivered to bus 1, this is just saying that it just simply increases the output of generator 1 by 1 megawatt. That's the marginal control. The marginal control for bus 2 is to get 1 more megawatt from the generator at bus 2, and the marginal control for bus 3 is to increase generator 2, generator 2 by 2 megawatts and drop generator 1 by 1 megawatt. So, and then the resulting LMP is just the sum of these changes times the cost associated with those changes.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.